Hi everyone. In the last class, we have discussed about characterization of closed range bounded operators, and today we want to discuss some more information about closed range operators. So we have shown that let T is in B of H1 H2. Then we have shown that range of T is closed if and only if there exists some constant K such that norm Tx is bigger than K times norm X for every X in null space of T bar. This is one of the characterization of closed range operators, and we have seen some more information about the relation between ranges and null spaces of adjoint operators. Today we want to discuss more about closed range operators. One important question we asked in the last class was, if range of T is closed, can we say that range of T star is also closed? So we are going to address that result. Let T be a bounded operator between H1 and H2. Of course, all the time will be assumed that all the operators that we consider are linear. Then the following are equivalent. First one, range of T is closed if and only if range of T star is closed. Okay, so let us try to prove 1 implies 2, 2 implies 1, again follows using the same trick that we used earlier. Apply the result 1 implies 2 for the operator T star and use the fact that T double star equal to T. Then we can get the implication 2 implies 1. Okay, assume range of T is closed. We want to show that range of T star is also closed. So let us take some Y from range of T star closure. Define a map phi from range of T into C by phi of, now every element of range of T is of the form Tx, where X is coming from H1. In fact, we have observed in the earlier class that we can take X to be in null space of T per, because any element of the Hilbert space can be decomposed as an element from the null space, direct sum with an element from the null space of perp. And we know that null space element is mapped to 0 only by T, so we can write this as inner product X with Y for every X in null space of T perp. So let us call this as equation 1. Now it is easy to check that phi is linear, and next we want to check whether it is bounded or not. So we have mod phi of Tx is less than or equal to norm X. X is coming from H1 and Y is in range of T star closure, that is null space of T per. So this is again in the Hilbert space H1. Now we know that since range of t is closed, we can get a constant. So range of t is closed implies there exists some k such that norm tx is bigger than or equal to k times norm x for every x in null space of t perp. So let us call this inequality as 3 by 2 and 3. So we get that mod phi of tx less than or equals to 1 by k norm tx into norm y1. So this implies norm of phi is less than or equal to 1 by k times norm y. That means phi is a bounded linear functional. Now we can apply the Ries representation theorem. By the Ries representation theorem, there exists unique z from range of t equal to null space of t star per, because range of t closure equal to range of t here, such that phi of tx is inner product tx with z for every x in null space of t per. But we know that by the definition this is inner product x with y. So this is, so that means we can say that inner product x with y is nothing but inner product tx with z by the above observation. This is nothing but inner product x with t star z, and this is true for every x in null space of t perp. So from this we can conclude that inner product of x with t star y minus t star z is 0 for every x in null space of t perp. So this again implies that y minus t star z is in null space of t, because y minus t star z is orthogonal to every element of null space of t perp. Now we know that y is coming from range of t star closure, that is in null space of t perp. So this element, and t star z is in range of t star, that is again equal to null space of t perp. So these are two elements coming from the same space. So since null space of t perp is a subspace, their difference must be inside null space of t perp. So here we can say that this is null space of t perp, which is equal to 0. So from this we can conclude that y equal to t star z, but that again implies it is in range of t star. So we have shown that we have taken y from range of t star closure and shown that it is in range of t star, hence range of t star is closed. So we have proved that implication 1 implies 2. To show 2 implies 1, replace t by t star, and using the fact that t double star equal to t, we can get the conclusion. So this completes the proof that range of T is closed if and only if range of T star is closed. Next we want to observe the relation between range of T and range of T star. So we have already proved earlier that range of T equal to range of T star. Now if range of T is closed, can we say that range of T star is closed? And again other way, if range of T star is closed, can we say that range of T is closed? In fact, we can prove that result. I'll write as a proposition. Let us take T from B of H1 H2, then range of T is closed if and only if range of T star is closed. So in this case, so we get range of T and range of T star both are same because of the above result, range of T closure equal to range of T star closure. So let us try to look at the proof of this one. First assume that suppose range of T star is closed. So we have range of T closure equal to range of T star closure, that equal to range of T star, because we are assuming that range of T star is closed. Now we know that this is subset of range of T. So now anyway this is subset of range of T closure. So we can conclude that therefore range of T and range of T closure are same. Now on the other hand, assume that range of T is closed. To show that range of T star is closed, we want to show that range of T star is closed. So enough to show there exists some m bigger than 0 such that norm T star x is bigger than m times norm x for every x in null space of T star perp. But we know that null space of T star is exactly null space of T star. Okay. Now let us start with an element from null space of T star perp. So let x be an arbitrary element from null space of T star perp. This is 2 because x is coming from null space of T star perp, that is exactly range of T closed. So when x is in null space of T star perp, then we can conclude that T star x is in range of T star, that is in null space of T perp. Now range of T is closed. Implies there exists some k such that norm of Tx bigger than or equal to k times norm x for every x coming from null space of T perp. But we know that T star x is in null space of T perp. So from we can say that T star x is bigger than k times norm Tx for every x in null space of T star perp. Now we know that range of T star is also closed, so there exists some L such that this is norm T star x is bigger than norm x for every x in null space of T star for some L, because range of T star is also closed. So this implies that range of T star is closed by the earlier characterization of closed range operators. So this completes the proof of that range of T is closed if and only if range of T star is closed. Now similarly we can write a corollary. Range of T star is closed if and only if range of T star T is closed. Actually we can summarize all the closed range operators results. Summary. Let T be a bounded operator from H1 into H2. Then the following are equivalent. Range of T is closed. There exists some number k such that norm Tx is bigger than k times norm x for every x in null space of T per. Range of T star is closed, and fourth condition is range of T star T is closed, and this is again equivalent to range of T star is closed. So these are the equivalent conditions for an operator to have a closed range. Okay. Now suppose T has closed range as well as 1 to 1. So next, range of T is closed implies there exists some number k positive such that norm Tx is bigger than k times norm x So if null space of T is 0, so then we can say that norm Tx is bigger than k times norm x for every x in H1. So when range of T is closed and T is 1, 1, we got this condition. Now suppose we get this condition, can we say that range is closed as well as null space of T equal to 0? In fact, that is trivial from this inequality. If Tx is 0, then automatically x is 0 by this inequality. That means T is 1, 1. And range of T is closed because norm Tx is bigger than k times norm x for every x, in particular for every x in null space of T per. So such an operator we call as bounded below operator. We say T to be bounded below if there exists some number m bigger than 0 such that norm Tx is bigger than m times norm x for every x in H1. So observation that we have already made, T is bounded below if and only if range of T is closed and T is 1 to 1. One simple example of bounded below operator is the right shift operator. R of En is mapped to En plus 1, where En is a standard orthogonal basis for the Hilbert space L2. So we know that norm of Tx, here norm of Rx equal to norm x for every x in L2. Hence, by the earlier condition or even by the definition, we can say that R is bounded below. Okay. So, but the left shift operator need not be bounded below. Is not bounded below. So show that R star is not bounded below. Okay. Now we can ask the question: is it the bounded belowness property? Is it related with the invertibility? So before discussing that, we can express the bounded below property in a different way. So now let me look at this definition. T is bounded below if and only if there exists a number m bigger than 0 such that norm Tx is bigger than or equal to m times norm x. Now we can say that you define a function define f from define f of x norm Tx where x is in h1 with norm x equal to 1. So this we call as a unit sphere. So f is defined from the unit sphere of h1 into c. So here s h1 set of all x in h1 such that norm of x is 1. We can say that T is bounded below. T is bounded below now f is a function. This is not linear. This is defined on a subset of the Hilbert space h1. So this is in the usual sense f is bounded from below. So this is a connection with bounded below operator and bounded below functions. Okay. Now we want to look at the information between the invertibility of an operator and bounded below property as well as closed range property. Let T from h1 into h2 be bounded linear map. If T is bijective, then by the inverse mapping theorem Now T inverse we can define a map from H2 to H1 defined on H2. This is also bounded. Of course it is bounded and linear. But if T inverse is bounded, then we can show that T is onto and one to one. That is, so when T is bijective, so T is 1 to 1 and onto. But this onto property we can replace with range of T is dense in H2 and it's also closed. So onto equal to and range of T is closed. Now we know that range of T is dense is equivalent to show that this is null space of T star per. If that is a full space H2, then T star is 1 to 1. So onto can be written as T star is injective or 1 to 1 and range of T is closed. So T is bijective if and only T is 1 to 1, T is 1 to 1 and onto, and T star is 1 to 1. So that means we can say that T is bounded below and T star is 1 to 1. Okay, so bounded below condition need not imply that bijectiveness of the operator, but if T is bijective, automatically T is bounded below. But to get the converse, we need that T star to be an injective operator. Okay, so let us quickly define one quantity for T in B of H. B of H1 H2 define gamma of T. Of course, we assume that T to be non-zero. Gamma of T is the infim of norm Tx, where x is coming from the unit sphere of H1 and Mt is infim of, so this is Mt, this is gamma T, infim of norm Tx, where x is coming from the unit sphere of null space of T per. Okay, these are the two quantities we can define when T is non-zero. So the first quantity is known as the minimum modulus of T. And the second one is the reduced minimum modulus of T. We can easily check that Mt is always smaller than gamma of T. Sometimes they may be equal also. We can easily show that range of T is closed if and only if gamma T is positive. And the third condition is T is bounded below if and only if the quantity Mt is bigger than 0. Okay. These properties of MT and gamma T we will be looking at a later stage when we discuss the spectral theory of linear operators. But these two quantities, both MT and gamma T, are useful in finding the closeness of the range of the operator as well as invertibility of an operator. So we'll be looking at these properties in detail at a later stage. Okay, so I'll stop here. Thank you very much.